Hello, everyone, and welcome to Module 5 of Multivariate Statistics. In this module, we talk a little bit about the most common regression assumptions, or a lot of these are sort of generally statistical assumptions that apply in a lot of different situations. And we also talk about what to do when those assumptions go bad, which is always an important question to consider. So, good topic this week. There's a lot to cover. We'll probably skip or chop this video up into two parts. There are a lot of sort of discrete assumptions that we are going to briefly talk about and discuss how to evaluate. So buckle in. It should be fun. All right, so a brief follow-up related to assumptions from last module. If you remember, in the previous module, we talked about repeated measures ANOVA. And several folks asked questions that related to the sphericity assumption. And this is indeed a very tricky assumption. You know, what does it really mean? What are you looking for? How do you interpret the results? What happens if that assumption is violated? Those are all really good questions. It is an assumption that you see from time to time that's addressed in the literature, and it's an important one to think about. So my response is, first of all, what is sphericity? Well, a measure demonstrates sphericity. Here's sort of a definition over here. If its variance is equal across time and its covariance with other time points is also equal over time. And this is what this looks like statistically. So this is what's called a covariance matrix. So it is sort of like a correlation matrix. And here we have test 1, test 2, test 3, test 4. We have 4 time points of the same measure. And instead of the correlation between time points, what I've asked the software here, this is Stata, although you can do something very similar in R using some of the correlation commands, is to give me the covariance, or in the case of the diagonal, it's actually the variance. So it's the variance of that measure at that given time point. So the variance of test 1 is 214, test 2, 189, 134, 146. So what is the variance? Well, in a statistical sense, right, it is a measure of the total variability, the sort of absolute spread and variability of a measure at a given time point. And so one part of the sphericity assumption is that the variability in your measure should be roughly the same across each time point. And so ideally, we would want these red numbers to all be pretty close to each other. That's one half of the sphericity assumption. The other relates to these purple numbers. Sphericity also assumes that the covariances, so example, the covariance between test 1 and test 2, is equal across time points. So ideally, we would see all of the purple numbers being the same as well. And if you look at it, it looks like this is a much harder assumption to meet. For example, test 1 and test 2 have a positive covariance, but test 1 and test 4 actually have a negative covariance. And so that's very different, right? If we assume that those numbers should be the same, but one is positive in a certain value and the other is negative, well, that's probably not very similar. And so this is one of those assumptions that can be really tricky. Now, is this assumption realistic for most longitudinal data in educational research, the space in which we work? No, you can probably guess that. People and learning are complicated, especially when people are learning, right? And things can change in unexpected ways. And so it's not realistic to assume that this assumption is met. So does that mean you give up and you never do repeated measures ANOVA? No. A repeated measures ANOVA actually has built-in adjustments for violating this assumption, and we learned about several of them. There was the greenhouse geyser. In Stata, there was the box adjustment. There's something called the Hoyne-Felt, the HF adjustment. In R, all of these things are tools for adjusting your estimates to correct for a possible violation of the assumptions. So there are ways to deal with this. And this is not unlike sort of paying a penalty in terms of degrees of freedom. And your estimates are sort of corrected or adjusted for possible assumption violations. Is this the best we can do for longitudinal data? No, and I do want to point that out. Um, this is sort of the simplest model for longitudinal data, but really the best way to handle longitudinal data is with some form of multi-level modeling or latent growth curve modeling, which is a bit more complicated to learn. But both of those also tend to make sort of more realistic assumptions about the data. They don't require the sphericity assumption, although they do require multivariate normality in a lot of cases. So there are other things. I teach a whole course in multi-level modeling. It's a very useful technique, particularly when handling longitudinal data. So there are other tools out there, but repeated measures ANOVA is a good tool for answering a very basic question. Well, not even that basic, but do we have change over time on a given measure? And that's a very reasonable tool to use in that case. All right. Okay, so another week, another fun Allison Hurst cartoon. I found this one on her GitHub repository. Thank you, Allison. I love these. So Allison, just like last week, we talked about the many stages of learning software. Allison also has one about the many stages of code debugging. So what is debugging? Well, that is dealing with all those red errors, right? You get an error, you're like, what did I do? Did I type something in wrong? Am I missing a space? So on and so forth. And I really liked this kind of progression of going from sort of, I got this at the beginning, and then you kind of have a lot of doubt in the middle, and then, oh my gosh, it's so maddening when you figured out it doesn't work. Some students emailed me about these exact problems over the weekend. I absolutely get it. I've been there. Then you have your zombie meltdown, and then a new hope, and then hopefully you're able to figure it out and make it work. So this is just to share that if you have struggles with your code, you are not alone. And it is certainly not an indictment on you as a researcher or as a coder or as someone who does quantitative research. We all struggle with this. It's one of the things that goes along with working in code. There are a lot of advantages to working in code, but there are a lot of challenges too. So hopefully you made it all the way through the cycle this week, but sometimes you do, sometimes you don't. All right, so let's talk a little bit about regression assumptions. So I included a YouTube link here just for fun. So some of you may or may not know I really enjoy the Harry Potter series. And there is a really great, both the books and the movies, but there's a really great scene in the movies where Harry, Ron, and Hermione go to their first divination class with Professor Trelawney, if you remember that, Professor Trelawney. Played wonderfully, I think, by Emma Thompson in the movies. And I just love that, they're trying to learn about what it means to practice divination, right? Kind of seeing the future and omens and things like that. And they're reading the tea leaves in their cup. So they drink, they sort of look at tea leaves, which is one of these techniques. And it's if you might have heard the expression, it's clear as mud, right? It's clear as mud. A lot of times that's what it seems like. It's like, I think I know what I'm doing, but I don't know exactly. I don't entirely know what I'm looking at. Things are not always clear. That's sort of what happens sometimes with regression assumptions. So I want to set you up with that sort of mindset that we're reading the tea leaves here with regression assumptions. We're going to do our best to try to unpack them and see whether assumptions have been met. But also, really importantly, we're going to learn about ways that you can do things like sensitivity analysis or bootstrapping to see that even if the assumptions might have been violated, it may not be as big a problem. So let's start with a concept called generalizability. This is a really important concept in quantitative research. So when we run a regression, the sort of inference that we want to make is usually to generalize the model that we get and the results we get from our sample to a larger population. Okay, so, and this can vary. Some of this is sort of the choice of the researcher. So let's say I go out and sample schools in the Richmond area, and I have this, cool sampling scheme where I'm, choosing schools that are representative of the Richmond region, and I'm asking kids using surveys, about their attitudes or beliefs or whatever that is. If I run a regression or really any kind of statistical model on those results, the argument that I'm making implicitly is that if I've done my homework in terms of my sample, if my sample that I've chosen is representative to the larger population, I want my results, my inferences that I'm making, my estimates, to also generalize to that larger population. That's the sort of essence of generalizability. And this is different in the quantitative world than the qualitative world. So generalizability doesn't really work the same way in the qualitative world. It's more about like trustworthiness and triangulation and reflexivity, and there are a lot of other concepts there that we look at to sort of evaluate the kind of trustworthiness of our results. And so this is just in a quantitative paradigm. But that's where the assumptions are important, because the assumptions technically need to be met in order to be able to generalize our results to the larger population. Otherwise, our results are very specific to the sample in which we are working. And so it's hard to make a larger statement about the phenomenon that we're studying and say, yes, this does apply not just in my sample, but in a larger sample or in some sort of a population. And so that's really the essence of assumptions. I know sometimes we see this word assumptions, we're like, oh my gosh, just a bunch of stuff we have to memorize and think about, and it's just really overwhelming. But I think it's helpful to think about the bigger picture here, which is the reason that we consider regression assumptions or statistical assumptions at all is because we often really want to make a case that our results have meaning beyond our sample. And that's really what generalizability is all about. All right, so let's break down some of the more straightforward assumptions. And I call these straightforward. They're not always super straightforward, but these are the assumptions that we can kind of check off as we go, that don't require typically a lot of digging, but just sort of confirmation. So first of all, if you're doing regular multiple linear regression, you need to be working with an outcome that is functionally continuous. So that basically means, right, that it's measured on some kind of an interval ratio scale. Now, we know that you can kind of fudge this a little bit. Some people use like a Likert scale as a continuous outcome. That usually works okay. But technically, your outcome does need to be continuous. So if you have a binary outcome, for example, yes, no. Let's say you're predicting whether or not someone chooses another person as a friend, for example, an example from social network research. That's not a continuous outcome, right? The number of friends they choose might be. That's actually what's called a count outcome. It's actually a little more complicated, but the sort of binary choice is not a continuous outcome. And so that would not be a good fit for multiple linear regression. It would be a good fit for logistic regression, which we're going to cover in a couple weeks. But in this case, the outcome itself must be continuous. The predictors in a regression model can basically be anything, which is really cool. This is another reason I really love regression. Predictors can be continuous, again measured on an interval ratio scale, or they can even be dichotomous, yes, no. They can be multiple categorical, they can be count variables, they can be pretty much anything. So that one's usually pretty easy to check off. There's this assumption of non-zero variance. So all of your predictors have to have some variability. So an example here, if you are interested in studying SES, for example, as a factor in a regression model, but your sample is composed entirely of kids who are in the highest, say, quartile of SES or the lowest quartile of SES, if there's no variability, that variable can't give you any estimates, because estimates can only be obtained when you have variance or variability. So non-zero variance is an important one, but that's, again, something you can check really quickly. And then this assumption of independence. Independence is an interesting one. It's tricky. So technically, all values of an outcome should come from a different person. So what this means is if you have something like longitudinal data, right, if I have responses from the same person over time, then I need to be really careful with how I handle that. Usually I cannot put that in a regular regression. I need to use something like multi-level modeling or repeated measures ANOVA to accurately partition that variability and account for the fact that I have repeated measures from the same person in the same model. Another important consideration of independence is this question of when participants in our research are clustered or nested. Okay, so an example here might be, when we have participants in classrooms, students who are nested in classrooms, those observations are really not technically independent, because all of those students, first of all, did not end up there randomly, right? The class selection is often not a random process. But the students in close proximity to each other often influence each other. So student scores in one classroom are often more correlated than scores between classrooms. And so independence becomes a very important consideration. All right, so those are the sort of straightforward assumptions that you can kind of think about. And they're mostly related to the types of variables that you're using and also the manner in which your data were collected. All right, so now the more tricky assumptions, and these are the ones that we typically test either graphically or statistically. And these also are much more wordy. These have longer names and more verbiage with them. So the first one is an assumption called homoskedasticity. And I'll say this is the kind of British form of spelling this assumption. It can also be with a K, so homoskedasticity with a K. This assumption basically means for each value of a given predictor, the variance of your error term should be constant. So if you take a predictor and you look at sort of all the values of that predictor on a scale, and you have the error term on the y-axis, you should have sort of constant variability. And if you're noticing, I'm defining that graphically, because typically graphically is the best way to define that particular assumption. We'll go into more detail on that in a moment. We also make this really important distinction of that the errors, or the error term, or the random variation left over in a regression model should be normally distributed. We call this the residual, usually. So when you calculate the residual from a regression model, those errors should be normally distributed when you look at it in a histogram or something like a quantile plot. There's also the assumption of no multicollinearity. So that means your predictors must not be too highly correlated with each other and with the outcome. We'll talk specifically about that. This, of course, does not apply when you are doing simple linear regression. So if you only have one predictor and one outcome, you don't have to worry about multicollinearity because you don't have multiple predictors. And then the all-important assumption of linearity. So there is this assumption that underlying this model that we're fitting actually is, in reality, right, in the population, there is a linear relationship. And I call this one a simple but deadly assumption, because sometimes it can be really hard to confirm. But there are ways that we can sort of test that assumption and see whether or not the model does appear to be more or less linear in its parameters. Okay? So those are the trickier assumptions. And each one of these we sort of break down and examine. So we have homoskedasticity, normally distributed errors, no multicollinearity, and linearity. We also have a nice set of tools for checking these assumptions. And almost all of these assumptions can be checked using residuals. So we'll learn how to calculate residuals and how to use them. So when we're assessing, and notice I use the American spelling here, when we're assessing homoskedasticity and linearity, one of the best things you can do is create what's called a residual versus fitted plot, or in Stata the command is actually RVF plot for that reason. In R we use ggplot. So you make a little plot here, and you can just literally look at it, and I'll show you some things to look for in the plot to assess that assumption. For normality of errors, you can use a normal probability plot, a quantile plot, or a histogram of the residuals, and that's also a great way to go. There also are a number of statistical tests that you can use that check these same assumptions. So that can be a little bit tricky. So you kind of have these two camps, right? So some people will say, well, if you want to assess the assumptions, you need to check plots and histograms. And I think if you took EDUS 608, you probably did a week where you did a lot of these. You looked at a lot of these plots and histograms. So the advantage of looking at things graphically is it's more nuanced. It lets you really look at things and see if things look strange and make an assessment. The con, though, is clarity. Sometimes when you look at a plot, you don't get that clear answer that we all sort of really like. If you like clarity, statistical tests are the way to go for assumptions. And most of these are new. They were probably not covered in EDUS 608. For a lot of these, you get a p-value. We love p-values, right? But a con, as with a lot of statistical tests, sample size plays a really big impact here. So a lot of these tests are underpowered in small samples. So that means they'll miss things that might be a problem. And they're also overpowered in large samples. So slight problems with the assumptions can actually not be, that aren't actually an issue, can look like they're an issue according to the p-value. So what do? You have plots and histograms, you have statistical tests. What the heck do you do with all this stuff? I love this quote from the State of Documentation. So they kind of address this. They say, so why bother with the various graphical commands when the test seems so much easier to interpret? In part, it's a matter of taste. Both are designed to uncover the same problem, and both are in fact going about it in similar ways. One is based on a formal calculation, those are the tests, whereas the other is based on personal judgment in evaluating a graph. That's the plots. On the other hand, the tests are seeking evidence of specific problems, whereas judgment is more general. So that's another thing we're weighing here too. And then they say at the bottom, the careful analyst will use both. And so that's the approach I'm going to show you, how to use both visuals and statistical tests and sort of weigh the evidence of both. All right, so some of you may have seen this slide already in 608. This is the way I used to introduce the concept of residuals in EDUS 608. So checking residual assumptions is kind of like going through the garbage of your regression model. I know it's kind of a gross analogy, but that's really what it is. So residuals are the variability that remains after you've removed all the information, all the sort of predictive power of your model. And so they're like garbage, right? Residuals are supposed to be something that you can throw away, and we assume that they sort of wash out overall in the end. But you have to make sure that you're only throwing away garbage and not anything useful that can be used to better explain the relationship. So sometimes there are things hidden in garbage, the residuals, that actually, for example, evidence of nonlinearity, which might really help us in specifying a better model and also ensure generalizability. So that can be a really important concept. The story I always tell is my brother in elementary school had a retainer. And if any of you ever had a retainer, right, they're really gross. But he was supposed to take it out whenever he was eating lunch. But he would a couple times he forgot, and he threw away his retainer in the garbage, right, with the lunch. And oh man, that way he was not very popular in my house when he came home and he forgot his retainer. He threw it away in the trash. And that would be an example of, right, something important that's in the trash that you actually would really want. So if my brother's retainer helps you think about residual assumptions, so be it. If not, sorry, that was probably just a really gross story. So yeah, we'll grab some gloves. We're going to use some residuals today and dig into things. Okay, so we're going to cover a few of these assumptions, and then we're going to pause. That's probably a good point to stop. So we're going to talk a little bit about some of these tools that we've already discussed and how they can be useful. So the first really useful tool in assessing assumptions is what's called a residual plot, or a residual versus fitted plot, or an RVF plot. And what is this? So this is basically a XY plot, a scatter plot, where you have the standardized residual And the residual, remember, is just the observed value of an outcome minus the predicted value. That's all it is. So it's, the score that I actually earned on the test minus the score that the model said I should have earned on the test. That's a residual. And then by standardizing, of course, we're just kind of fitting it to a kind of mean 0, standard deviation 1 kind of scale. So this is the standardized residual on the x, and then on the y is the predicted value. So these are predicted values of our outcome, higher being higher scores, lower being lower scores, and then these are the residuals. So when we look at this, now this is a tough concept. Andy Field puts this well, I think, in his book. So Andy says if everything is okay, then this graph should look like a random array of dots. If the graph funnels out, then it's a sign of heteroscedasticity, and any curve suggests nonlinearity. Now, unfortunately, we as humans are actually really bad at detecting things that are actually random. So this is not our strong suit as human beings. But there is sort of a sense when you look at it, you kind of are looking. It should look like a cloud, kind of a random sort of cloud. And any evidence of funneling, so that's where the values funnel, kind of in a triangle, and it can be in a lot of different ways, depending on the shape of the plot and the values. And curving is just what it sounds like. It's kind of evidence of a curve in the plot. So funneling is evidence of what's called heteroscedasticity, which is the violation of homoscedasticity, and curving is evidence of nonlinearity. So that's what we're looking for. So just a refresher here from 608, homoscedasticity is the good thing. That's what we're looking for. And that means that for each value of a predictor, the variance of your error term should be relatively constant. The violation of that is what's called heteroscedasticity, and that's a bad thing. And that means that the variance is not constant across all values of a given predictor. And that would be a violation of the assumption. We usually check it using an RBF plot, and we're looking for funneling here. So this is an example where we don't see a lot of funneling. So if I take my pen here and I kind of trace around this cloud, I more or less don't see a funnel pattern. It just kind of looks like a square, rectangular, oblong kind of cloud of points. And that's a good thing. That probably means there's not a violation of the homoscedasticity assumption. Here's an example of a plot that is definitely heteroscedastic. All right, so if I draw an arrow around this, I'm pretty much looking at a funnel going from left to right. And what does that mean? Well, the closer that points are clustered together, ideally around 0, means that a model is doing really well predicting a given outcome. Because basically, the predicted value down here has a very low residual. But as we go from left to right, the residuals get wider and wider, which means our band of prediction, we're essentially getting worse. So the model's actually doing worse predicting people with higher fitted values or predicted values than it is for people with lower. And that's inconsistent prediction. That is not something that we want in a regression model. We want our prediction for this person here to be on average roughly the same level of accuracy for a person who's way out here in terms of the fitted values. So that's why that is a big problem. There also are statistical output that we can use for this. So in Stata, this is called HET test for heteroscedasticity test. The longer name here is the Bruch-Pagan-Cook-Weisberg test for heteroscedasticity. It's a mouthful. Basically, all we need to know here is that this thing is testing the null hypothesis that there is not heteroscedasticity. And so if we see a low p-value here, that's a bad thing, because it means that there's evidence that there is heteroscedasticity. So in this case, a p-value of 0.6558 is a good thing. It means that we do not have heteroscedasticity, or at least we don't have evidence of it. In R, there's a very similar test, the studentized Bruch-Pagan test. Again, you just get a p-value and you plug in the model that you ran. So the function here is BP test, and it comes from the larger package called LM test. And that, again, gives you a chi-square value, a test statistic, and a p-value. same thing. Okay, so linearity. This is another concept that we test using a RVF plot. So we assume that our outcome and predictors are functionally linear. That's a good thing. It means that we can model their relationship basically with a line or a plane or something linear. And if the linearity assumption is violated, that means you have evidence of nonlinearity. So nonlinearity is the bad thing. And it typically means that your relationship might not be modeled with an exactly straight line. There might be a quadratic relationship, an exponential relationship. Maybe you have a predictor that's missing or misspecified. Basically, we might need another kind of model to accurately represent it. In the RVF plot, it means we're looking for curving. So this is that same example. Again, there's no evidence of curving here, but we're looking for sort of a trend up or down in the points that might look like a curve. So here's an example. I call this the Star Trek plot. This is a very nonlinear curve. It may actually also be heteroscedastic, although it's mostly nonlinear. So that's evidence of nonlinearity. That means there's something going on in your model that you're not fully capturing. Okay, so then we'll talk about normal distribution of residuals. So we assume that our residual and error values are normally distributed, and that's a good thing. So what that means is when you predict your residuals after a model and you throw them on in a histogram or a probability plot, they should be normally distributed. So we should have a normal distribution. If we have not met this assumption, the sort of bad thing, the violation of that assumption, is called non-normality of errors. So that's the bad version. And that means that there may be outliers or other influential observations skewing your results, or maybe the model's misspecified. It could mean, a lot of different things. So again, to assess this assumption, we basically look at a histogram of the residuals. And what we want to see is that the residuals appear normal and that they're centered on 0. So this would not be a great example. In this case, we see we have far too many observations just to the right of 0. So that's definitely evidence of, let's see, that is not, that's kurtosis, right? This is a violation of kurtosis. And we also see a little bit of a skew. So we have too many observations over here on the right side, sort of positive outliers, and we probably have too few observations over here, which are sort of negative values off to the side. So there's a lot of things we're looking for here, but this does not look great. When you look at the distribution of an outcome, something you're treating as an outcome, oftentimes we're much more forgiving about things being normally distributed, because really the assumption is not about the outcome, it's about the residuals. So the residuals are the thing we're really worried about, and we do want that to adhere to as much as possible to a normal distribution. So here are some fun examples of non-normality. You can have a heavy uneven skew over here, lots of outliers below -2. You can look at this either with a density plot or a histogram. They both give you basically the same information. And then, of course, Allison Hurst helping us out here, too, with a fun visual of non-normality. You can also use what's called a normal probability plot or a quantile plot. So basically, this is just taking the projection of the scores and putting it on a probability plot. And so what you're looking for here is ideally all of your dots sort of fall perfectly along this middle line here. And the extent to which they don't means sort of deviations from normality at these different points in the distribution. It doesn't have to be perfect, but large or systematic deviations are generally a problem. So here's a example of a good normal distribution, and this is when something would be relatively bad. So you see this sort of systematic deviation in that assumption. So that's definitely not a good thing. There also is a statistical test for normality called the Shapiro-Wilk test that works pretty well. So it's a single statistical test for normality. It gives you a p-value. We love p-values. And if the test is significant, it means your residuals are likely not normally distributed. So you can use actually Shapiro-Wilk for any kind of test of normality. It doesn't just have to be residuals, but yeah, you get a test statistic. You actually get two test statistics, and then a z-value and then a p-value. So what you're really looking for is this probability here. In Stata, they have a different test called the S-Francia test for larger observations. I don't know if there's an equivalent in R. It usually doesn't make a big difference, but in Stata they do make that recommendation. And here's the Shapiro-Wilk test in R. Again, here's your p-value up here. And if again, R loves scientific notation, so this is just basically really, really small. So it's 0.000002. So this would also violate the normality assumption. Okay? So what do we do when assumptions have been violated? This is a tricky question. So how do I know how much is too much, right? So how do I know if this is really going to cause a problem? Well, there's this famous quote from the Supreme Court, "I know it when I see it." And it actually comes from a really wild case called Jacobellis versus Ohio. And Supreme Court Justice Potter Stewart made this a long time ago. And what I like about that is, there's this idea of a judgment call, even in cases of the law, right, where you kind of have to deal with shades of gray. And there's Justice Stewart. So the more things look wrong, the more likely those assumptions don't hold. So in a way, you kind of have to trust your judgment a little bit. If you're seeing multiple issues, right, if you're seeing non-normality, if you're seeing issues with residuals and so on and so forth, that can definitely be evidence that there's something going on. But there may not always be clear evidence like, oh yes, this crosses the line, there's now an assumption, violation of assumptions. And so the key is really just to sort of think about how you might demonstrate using bootstrapping or other things we're going to talk about later, that even if there are violations of the assumptions, they don't impact your results, because that's really the key. So if there are some small violations, but they don't impact your results, then it's less of a problem. All right, so I'm going to stop there. We're going to talk about regression outliers, and then we're going to talk about bootstrapping in the second part of this video. It might be a little shorter, but this seems like a good stopping point. Hopefully it's been helpful so far, and we'll talk to you soon.